Okay, let's begin. So one more reminder for students and postdocs, please fill up this form if you want to present a poster or give a short talk. This will be on Thursday. So given, depending on which one we have a more subscription for, we'll go with that option. Even if you have already filled up the older form, we request you to do it again. Please fill it up by tonight, okay? And right, okay, so let's start. We have Piyush again continuing with, sorry, Pravesh. Yeah, I'm underslept.
It's my usual excuse.
Yeah, we have Pravesh continuing with, I thought it was going to be Kikuchi reloaded, but it's something else. Okay, proofs and algorithms.
Okay, yes. Yeah, thank you for showing up to the morning again after yesterday. Yeah, I want to talk about something completely different because I thought I tried your patience with Kikuchi enough yesterday. So I'll tell you about a method of algorithm design, which now goes by the name of proofs to algorithms method. I'll explain what that is by means of a couple of examples in the talk. And at a very high level, you can think of this method as a way to come up with a semi-definite programming relaxation along with its analysis, like why does it work, the rounding algorithm or whatever, together, right? So for those who might have seen some applications of semi-definite programming, for example, if you've seen the Gurmanson-Williamson's algorithm for approximating max cut, you might know that there aren't as many classical applications of SDPs compared to, let's say, linear programming. And one of the reasons is that it was, at least in the beginning, difficult to come up with new SDPs for relevant problems along with their analysis. In general, like it's easy to come up with an SDP because it's a relaxation. I can write one for like many problems, but to come up with an analysis, to come up with a rounding algorithm and why it works, how good it is, was somehow, at least sociologically speaking, more challenging than, the context of linear programming. And so one upshot of this method is that in the last 10 plus years now, there's been like a proliferation of algorithms based on semi-definite programming. And they use this recipe where somehow, a more natural, more intuitive story-like method to come up with SDPs and rounding algorithms, etc., follows from like one principled way of thinking. And so I'll explain like the subtitle by means of an example as I go in the talk, but at a very high level, it refers to the same phenomenon. Like, SDPs and their analyses were so rare that every new SDP used to have its own name, at least till around like 2008 or 9. The Gurmanson-Williamson SDP was, of course, the GW SDP, but there was the Gurmans-Lineal SDP. There was the nuclear norm minimization SDP for like solving the matrix completion problem and so on and so forth. And when you have to name a new object, you remember you do it because it's rare, right? Like you have to give it a name because the name identifies it. And one reason we have stopped naming our SDPs, our SDPs don't seem to have name anymore, right? Like we don't call them Gaussian mixtures SDP or whatever. And one of the reasons is that there is a principled story to come up with it, and because they are kind of on demand and we can do them much more easily now, we don't actually give them their own names. Okay, so I'll tell you how this particular method is, at least in my opinion, non-trivially responsible for causing this proliferation of SDPs to an extent that we don't have to name them. Okay, good. All right. So at a very high level, I want to explain this method to you. Right, this method of coming up and analyzing semi-definite programming relaxations for algorithmic problems. Now, the method is applicable slightly more generally, especially now, but I will focus on one specific kind of problems. At least most of the spiel I will tell you today would be relevant to solving this so-called noisy signal recovery problems. And again, I'll explain by means of an example what these are all about. But these examples include some things that you might have seen before, like if you've seen compressive sensing, like recovering sparse vectors by means of less than dimension number of linear measurements. Like that's an example of a noisy signal recovery problem. If you've seen matrix sensor completion, dictionary learning. Today's talk is going to be about applications in high-dimensional robust statistics. That's also an example of a noisy signal recovery problem. If you've seen like problems that come less from like statistics and more from algorithms or like average case complexity, then problems like planet click, random and planet SAT that we saw yesterday, community detection that Prasad spoke about, the stochastic block model, semi-random versions of these problems, and they're all like also examples of noisy signal recovery problems, and this framework, this spiel applies to such problems. Of course, it goes beyond them, like, such problems arise also in cryptography, for example, attacks on various kinds of pseudo-random generators and such. And like, at least in the last few years, it was a long-standing kind of a dream of mine that we are doing a lot of this kind of a technology as applicable to average case algorithm design. But that, this kind of a new insight should eventually be helpful to go back to the old questions that we were interested in approximation algorithm design, and see if we can, at least say something interesting there. And at least like in the last few years, there are some instances where we can do even this. So I won't explain these connections, but the same approach seems to be useful for designing algorithms, even in, more canonical worst case approximation algorithm design settings, okay? So this is just to tell you that, what I'm telling you about and what you have to bear me for 2.5 hours for is somewhat worth it, hopefully, okay? Good. So let me tell you about the class of problems we will look at, in this talk specifically. They're all examples of parameter estimation problems, namely statistical parameter estimation problems. And they have the following structure. So, they all somehow correspond to you being given like a bunch of data points. Usually these are high dimensional data points, so they're d-dimensional here. You should think of d as large. So given like n data points in d dimensions, and you are interested in recovering structure, like there is some hidden structure in these points, like, we usually encode this structure also as a bunch of real parameters, let's say a p-dimensional vector valued parameter theta, and you are tasked with recovering them, okay? And why is this possible? Well, the data must have information about theta inside of it, okay? And you imagine that this information about the parameter you're trying to recover is encoded into the data by means of like some generation process. So you actually imagine that the data was generated by some process where theta was first selected, like, some arbitrary set of p real parameters. And then there was like some, modification, some process to use this theta as parameters of a probability distribution to generate samples from, and that's how xi's were given to you, right? So in some sense, you can think of like the theta to x transfer as like the generation process, like takes a bunch of real parameters, outputs a bunch of samples from a distribution. And your goal, the algorithmic task, is to reverse this process. Look at the data and like figure out the underlying parameters up to some approximation, etc. Okay? Yeah, somehow the slides seem to be slipping away from me. Good. Okay. So we're going to be interested in such problems, but this is not the very first application of SDPs to such problems. I was giving you examples like this before. So this is you don't need to read this theorem, but this particular SDP is called nuclear norm minimization SDP. And it was invented in the context of the matrix completion and relevant related problems. And this is actually also a long line of work, very celebrated line of work due to Candace and Recht, and then like lots of follow-on works. And what they proved is that there is basically a optimal algorithm in terms of recovery guarantees for this problem, and that involves solving this SDP, okay? And so this is an example of a parameter estimation problem. Like the parameter happens to be a matrix. The observations happen to be like, samples of entries of the matrix, and you're trying to recover like, the structure happened to be like, some low rank structure in the underlying matrix, okay? So this is an example of a same kind of problem that I wrote on the previous slide, and that goes back to, I don't know, 20 or so years ago now, right? But yeah, I was saying, as I was telling you in the beginning, like, analyzing and designing such SDP was kind of an art. That's why you gave them names. Like you came up with specific SDPs, you came up with specific clever methods of analysis, and you were able to make these kind of guarantees hold true, right? So today, I'm going to tell you about this proofs to algorithms method. And I think, in my opinion, like the origins of this method go back to this really important paper of Barak, Brandau, Harrow, Kellner, Starrer, and Zhu, which I don't know if it's public yet, but will win the Test of Time Award this year at Stock, very well deservedly. So this is the paper that, in some sense, began this whole paradigm. And of course, like, this talk is about how this method is actually useful in solving problems that you might care about. Okay, so yeah, over 10 years, this method has been like super useful for many problems, and I'll show you how it's useful today for statistical estimation problems. Okay, so let me tell you like a very high level view of how this method works. So in general, when you're trying to understand a parameter estimation problem of this sort, like you have a bunch of data points and you want to extract the underlying hidden parameter theta from it, right? And you have like some unknown generation process, like, some known, but like you don't know theta, right? Like you have some known generation process that transforms theta into excis, and your goal is to somehow undo this process, right? So usually when you think about these questions, you think about two questions. The first step you think about is there enough information in the samples to uniquely, up to some small error, identify the hidden parameter theta that you're interested in? Right? Like, is it even possible, looking at the samples, to gain information about theta? For all we know, there was no information at all, right? And the step that people use to establish that there is enough information actually has a name. In statistics literature, it's called proving unique identifiability. Like, basically the name is kind of self-explanatory, says that, I can uniquely identify the unknown parameter theta given the samples, as long as the sample is large enough, right? And that whatever is the amount of samples required is called the sample complexity of the problem. Now, importantly, this is a information theoretic argument in the sense that you're not all that concerned about efficient algorithms to calculate theta in this step. You're simply arguing that there is enough information, at least if I were to run some kind of a natural brute force process like maximum likelihood estimation or whatever, then it will like succeed. You should think of this as the analog of the Bayes optimal estimator from Prasad's talk yesterday, right? Like that would be the analog. There is always an estimator, like the Bayes optimal estimator, that proves to you that sufficiently large sample or whatever in this context will have enough information to recover theta, but in general, it won't run in polynomial time. And so therefore, there is a second step where you like somehow, think about how to come up with an efficient algorithm to come up, recover theta. Now, usually there is like a natural way to identify, like, prove unique identifiability, which is like do some kind of a Chernoff union bound or covering argument. Show that, somehow appropriately discretize the space and argue that, somehow you can rule out all but the correct sample. This is like, kind of a standard blueprint. If you've seen any like, basic machine learning, class or whatever, you would have seen like this kind of an argument in the context of a generalization bound, okay? So the point is that this is like, some simple probabilistic argument in general. It's not always that it is easy, but, in most cases it happens to be. The second step often is completely removed from the first step. It doesn't resemble all that much how you come up with, the proof of identifiability. You go back and think about, what structure in this problem might be efficiently exploitable by an algorithm and so on and so forth, right? So in general, even though unique identifiability is necessary for learning, in general, it's not sufficient. In fact, the ideas that go into it may not even be relevant for designing algorithms in a generic situation, okay? But what we will see today is kind of an approach that links these two steps more closely together, okay? So the punchline is that if we force ourselves to do a specific, simple kind of proof of identifiability, like you cannot do any of the usual arguments that you're used to in generalization theory. You instead, you have to argue, unique identifiability using some, I'll explain what the simplicity notion is later. But if you argue this, unique identifiability in some specific simple way, then, you would get an algorithm for free, okay? Now, this is, of course, tautological if I say it this way, because you say, like, analysis of an algorithm is, of course, a proof of identifiability, right? Like, it clearly proves it. But I'll show you how this whole connection is meaningful. It's not just like, tautological restatement of finding an algorithm, okay? And so, in some sense, this idea of proving or giving simple proofs of identifiability and deriving an algorithm out of it is basically the reason for the name of the talk. That's the proofs to algorithms method, right? Like you're transforming a proof of some statement to, algorithm, okay? And somehow the reason this approach is useful because these proofs often actually look like the proofs we usually would do. It's not a kind of proof that we wouldn't naturally do. It's a kind of proof that, usually involves a bunch of functional inequalities that we naturally use in analysis. And the punchline is that often you can take these proofs that you would have done naturally and just basically get an algorithm out of it without much additional work. Okay, and I'll explain how this works in an example today. Good. So the very high level message that underlies this, whatever, 10 plus years of work is you can reduce the design of efficient algorithms to finding simple, and this is the notion of simplicity. Again, this will become clear later. Low degree sum of squares proofs. So particularly simple proofs of unique identifiability. Okay, that's the punchline. Good. So this slide is to impress you that there are many, many applications. I'm not hoping, in fact, I will suggest not to read it all, but I'm just trying to show you that there's a lot of applications, and I think I missed several. So there are lots of applications, and they continue till this day. Okay, so there are like amazing papers that are appearing in the last 2-3 years, which continue to use and develop this method further. So hopefully, you are interested in learning more about it. Let me also give some resources. I will continue to self-advertise in the sense that if you want to see this method in action in much more detail, there is like somewhat dated course that I taught in I guess 2020 to 2021, and there are video lectures online, including assignments and some comments and whatnot. That's available. This is like some videos from a lecture series that Prasad taught at Simons Institute. And I think he, in fact, also uses robust statistics examples to teach sum of squares. He uses a different specific example of a problem, but I think I also recommend that. There is an even more dated course that Boaz, David, Pablo Perillo, and I taught that was from 2016, and the notes for that are also online. And today I'll present a argument which actually doesn't appear in a paper, but it appears in like this survey type thing that we wrote with Noah Fleming and Tony Pitasi. Okay, so anyway, so I'll post the slides and hopefully the references can be useful. Okay, good. So here's my plan, okay? I want to explain this method to you, and I'll explain it by means of an example. The example is going to be learning mixtures of Gaussians, okay? I'll tell you what this problem is very soon, but in general, it's kind of a nice and well-studied question in statistics and algorithms. So we'll use this as an example to design algorithms using the sum of squares method, this proofs to algorithms method, okay? You'll see somehow that, so in yesterday's talk, I guess probability and algorithms played a role, but there is also geometry in the title of this workshop. So actually in the first part of this talk, we'll continue to only talk about probability and algorithms. And you'll see in some sense, how this sum of squares method reduces the task of learning mixtures of Gaussians to basically getting some algorithmic analogs of concentration phenomena. Okay, so that's like an algorithmic lens on things that have been studied very well, for a very long time in probability theory. Okay, and then towards the end, this will be a sketchier part on the non-spherical Gaussians. So this will be about like spherical Gaussians where all the covariances are like identity-like. For the non-spherical case, we'll see that some geometry will play a role. I'll hopefully get to that point. And okay, yeah. If you're willing to extend me that long a leash, then sure. But I'll say at least I'll be able to draw more pictures in the third part. So there'll be like plane geometry happening. Okay, or like high dimensional geometry projected on the two-dimensional plane happening. Okay, good. So all right. So let me tell you about this problem. Okay. By the way, I'll soon. Akash has told me several times in no uncertain terms that I'm supposed to use the board. Which I will, but I want to get through all the cumbersome things to write on the board and focus the board usage on like more cool math stuff. Okay, so let me tell you the problem and the result, and then we'll do all the actual stuff on the board. Okay, so let me tell you about this problem of learning mixtures of Gaussians. And actually, I'll start with just the spherical case. In fact, we'll start with an even more special case, where all the covariances are going to be identity. So let's imagine the following question, okay? Your input, just like the general setting I told you, is a bunch of data points, x1, x2, xn, in d-dimensional space, okay? And you imagine that these data points are distributed as one, this measure of Gaussian density. Let me explain to you what that means instead of like trying to read a notation, okay? This is a distribution parameterized by k different d-dimensional vectors, namely the mean vectors, mu1, mu2, up to mu k. These are k unknown means of, k different centers, k different, clusters, if you will, okay? You draw a point xi in this sample as follows. You first choose one of the k mu i's at random, okay? And then you choose a sample from the Gaussian distribution with that chosen mu I as the mean and identity as the covariance. That's what this generation process is. So you just repeat for every sample this process independently. So roughly speaking, at the end, you'll have about 1 in k fraction samples from each of the k constituent Gaussians, okay? Your goal is to recover the k clusters in the points underlined. Does it make sense? So, you can imagine that because there are k different Gaussians, you might suspect that it is possible to identify cluster centers, etc. And that's what your goal is. Now, there is some difference between identifying means and identifying clusters. Let's keep it vague for now, and we'll get to more specific soon. Okay, so here is a picture. It's a two-dimensional picture. I guess geometry has started happening right here. So okay, this you can think of like a two-dimensional mixture of 4 Gaussians, right? And this circle is supposed to indicate that the variance of every one of the clusters in any direction is the same. Okay, so it roughly looks like this. Good. All right, so this is a very well studied model. In fact, arguably it's the very first model that people started looking at the beginning of modern statistics. And this is like, it goes back to Pearson in 1894, who actually used mixtures of Gaussians for application to biology. It's a very cool application that I won't tell you about today. And it became like a really important question because of its applications. And in particular, there was like this heuristic called the expectation maximization heuristic that Dempster, Lyard, and Rubin invented. And that led to its usage in practice a lot more. So, none of these were provable algorithms. The provable algorithms really began with this very nice work of Sanjoy Dasgupta. So let me explain this line of work, because this is where in some sense the story of provable algorithms for this model begins. Okay. So if I want to cluster a mixture of k Gaussians, okay, you would imagine that it will be impossible to actually find these clusters if 2 of the means happen to be very close to each other, right? In the limit, if they are literally the same, of course, I can't tell one from the other. So you'd imagine that any method that can succeed in clustering these data points must rely on some kind of separation between the means. Okay, so we'll define this separation in terms of the minimum L2 distance between any distinct pair of means. Okay, that's what this delta is. And what this diagram is trying to do is plot the running time of the best known algorithm for clustering a mixture of k Gaussians as a function of how well separated the underlying pairs of means are. Okay, and so what Dasgupta did is like, actually his separation was kind of out of scale here because it depended on the dimension d. But basically his stuff started this work, and I think there was a long and quick sequence of works here, which culminated in this very nice work of Santosh and Wang from 2002 that basically showed that you can actually cluster a mixture of k d-dimensional Gaussians as long as every pair of means is separated by at least k to the 1/4. And the way to appreciate this is that the separation doesn't depend on the dimension at all. Like, it only depends on the number of components. So if k is very small, then no matter how large d is, it's like a fixed constant separation suffices, for example, right? Like, that's how you should think about it. But of course, you could ask if this is the right value of separation. And by the way, I should say that this is actually an improvement over the time. So there was a k to the 1/2 in between, a d to the 1/2 in between, and so on. But so this result of Santosh and Wang, actually, it's a very cool result. It's one of the first applications of SVD in algorithm design, so dimension reduction, if you will, right? So like a lot of cool ideas go into it, like things that now we think of it as second nature, but they were happening in this very cool paper. So that was like this result here. And then for a while, this question of whether we can beat this separation, basically had no answer. We did not know. In fact, for a while, like we did not know where, in fact, even the statistical threshold for this problem lies. Like, what is the minimum amount of separation where I could at least expect a polynomial sample algorithm to exist for the problem? And this was kind of answered in this very nice work of Regev and Vijay Raghavan in 2017, which is like at the time I got interested in this problem. And they proved that, actually just square root log k separation suffices. Right? Like, so there's kind of a huge gap between this k to the 1/4 and root log k. And so now there was a natural question, like, are there algorithms that approach this root log k statistical minimum separation required? And so, that's what we did in this 2017, actually published in 2018 work with Jacob Steinhardt. We basically showed that, so actually at root log k, we actually only get a d to the log k algorithm, not a polynomial time algorithm. But basically for any k to the epsilon, we got a polynomial time algorithm whose exponent is like, some function of epsilon. It's like 1 over epsilon or something. Okay, that's what we did. Actually, at the same time, there were 2 independent results that proved a similar result from this measure of Gaussians, spherical Gaussians problem. They more or less achieved the same result. In fact, Hopkins and Lee's paper was in fact also using the sum of squares method. So even the method was common between this result and ours. This Diaco-Nicholas Kane Stewart was not using sum of squares at the time. Over time, I've convinced Ilyas that he should use sum of squares too. I should say, like later on, like a lot of stuff has happened since then. So actually, this d to the log k turned out to be not necessary. In a very, very cool paper, Jerry Lee and Alan Liu figured out how to get a polynomial in D and K algorithm with a little bit additional loss over the minimum required separation, but it's still great. Okay, so yeah, so it's this is kind of the story, and I'm telling you, like in some sense a very dated version of it today to tell you about the sum of squares method. Okay, good. So actually no, I'll hide this under the rug, but yeah, this one is not SOS. In fact, there are other differences, like this result actually is slightly, I guess, considerably less general in its applicability than what I'm going to tell you about today. But the punchline is that at least for mixtures of Gaussians, this problem I wrote down here, they basically get essentially the right answer. Okay, good. So let me tell you how this result is actually more general than it looks, and this is what I was very excited about. And this, it seems like sum of squares gives it for free. Yes.
Sorry, I guess you mentioned that log k is like a
Yeah, it is a threshold. So I should be careful. The threshold is not sharp as far as I understand it, but it's like the threshold we know is constant times root log k.
Meaning it's not even about computation.
Yeah, that's the statistical threshold, right? Like below, like the point is, I think in some sense, if you think about it, it's not so difficult to see why this is the right number. If two means are, in some sense, if two means are closer than root log k, and each cluster is like 1 in k chance. So in some sense, the root log k is coming from the fact that even a standard Gaussian, if I take 1 over k part in the tail, it can look like a distribution with mean root log k. Like that's basically what's happening. That's what's governing it. And so it's not very precise in terms of what constant sits in front of root log k, but yeah, to at least asymptotically speaking, that's the threshold. Yes. Yeah. Yeah, very good question. What you're asking is, if I just want to like output a distribution which is close to the mixture of k Gaussians in total variation distance or something, so then clearly, no separation is required, at least information theoretically. And let's see. Santosh, do we know an algorithm like this? Yeah. Yeah. Like that's exactly the question. Yeah. Oh yeah, I see. Yeah. So yeah, I'm not 100% sure about this. So definitely separation is not required. It should not be, because you don't care about separating between two different means. And I think Santosh is, I think we should trust Santosh on this. And there seems to be a result. It seems that where poly D is possible. But yeah, I don't recall the reference of the top. Yeah. Any other questions about the result? Okay, good. Let me tell you a little bit more about why this result is like a nice illustration of the sum of squares method. The reason I'm choosing it, you'll see, like in some sense, even though we started to solve this problem, the result that we'll get would have like more nice properties than we bargained for, right? Which is kind of always nice. So how is it nice? Well, one, it actually doesn't require Gaussianity at all. Once you go back and look at like what it actually needs, it needs like some property. We'll get to it during the talk, and that property will show actually is satisfied by a large class of distributions. So at the time, Jacob and I proved that it's satisfied by any distribution that satisfies a Poincare inequality with dimension-free constant. Okay, that's what we proved. But as of this year, which in a result that will appear in this talk, Diaco-Nicholas, Hopkins, Pensia, and Teagle, they proved that that property actually holds for every sub-Gaussian distribution. So basically, the same result, literally the same algorithm with no change. We don't have to backdate our paper or whatever. The same paper, the same algorithm with the same analysis works for mixture of any sub-Gaussian distributions. Okay, this is, by the way, one of the great things about designing algorithms with sum of squares method. You can often pinpoint a very clean property that governs the success of it, and then you can like study that property to death without ever looking at the algorithmic application. And so if you improve the status of that property, you basically upgrade the results. And this is not the only example. There are many examples in this line of work where this happened. Okay. So you should think of like this class of distributions as like sufficiently light-tailed. Like you're always saying that the distribution shape doesn't matter. It's like moments or whatever doesn't matter. As long as it's like tails decay like a Gaussian, that's enough for this cluster. Okay. Good. So in fact, like it doesn't even need the model to be spherical for the result I'm stating today. As long as the spectral now, the covariance matrix is upper bounded, its largest eigenvalues, let's say at most a constant, the same thing will work. So we don't need sphericalness all that much. And in fact, the same algorithm will also handle adversarial outliers, which by the way was the main motivation we were looking at this problem at the time. We just happened to realize that people did not know how to solve this problem even without outliers. So that was great. But like, the same algorithm succeeds even if there is a constant fraction of, completely arbitrary outliers in the data. Even then we can give the same kind of guarantee. Okay. So yeah, today I'll not present the proof that we came up with Jacob, but I'll tell you a different proof that appears in this monograph I was showing you earlier with Noah Fleming and Tony Petassi. I think it's like particularly nice if you're teaching because it shows that there's one single lemma that basically gets you the result. Okay, good. So let's see how the algorithm for this problem is going to look like. So let me first describe to you the SDP we will use. So the SDP appears on this slide, and I'm now going to explain to you line by line what it does. That was a joke. That's not what I'm going to do. Okay, the SDP that I've written out here is actually the right SDP. This is the SDP we'll analyze. But the reason I'm showing it to you on a slide is that if I were to tell you the SDP and then say go and analyze it, you will never think this is even possible. It seems like a ridiculous task to look at this like, I didn't manage to write down the whole set of constraints. I got a bit tired in between. Okay, but we'll see that, I'll tell you a story where you will never have to look at this sequence of symbols ever again, and you will still be analyzing this SDP. Okay. Good, okay. So instead I'll tell you this so-called certificates first approach where, in some sense the SDP will pop out naturally from the analysis. So we'll first analyze something and that analysis will give us the SDP, okay? Good. So here is how we'll think about the problem. Instead of trying to find an algorithm, we'll try to solve the question of verifying a good solution, okay? It's a little bit like, you're taking a complexity theory class and then you decided to use what you learned in the class to design algorithms. Not always advisable, but today we are going to do that, okay? So imagine that, you want to take a solution, a purported solution, and design some test for it that convinces you of its correctness, okay? That's what your goal is. So, what would you do? Well, you have to do some checks. I'll do some checks, I'll do some tests on, solution along with the input I was given. And if the checks pass, I will declare that the solution is a good one. If the tests fail, I'll say, okay, it was a bad solution. This is what I want to do, okay? So this is what we'll focus on for most of the talk. And the way you should think about it is that if you approach with this method to solve a new problem, this will be the bulk of your work. In some sense, this will be 90% of your work. You'll simply think of like how to design a test or a checker for, solutions. And then, you work hard to get a test whose analysis is simple. And once you do that, the rest of it is largely black box. Okay, this is basically the message. So I will, of course, open up the whole black box for you today. But the message is that you don't have to do that part over and over again when you look at a new problem. Okay, good. So, all right. So this is a question of how can you recognize a purported solution. And in some sense, once you design a test like this, the test has two properties. It has like a completeness property and a soundness property. Completeness says that if it's a correct solution, I should accept. Seems reasonable, right? The test should accept good solutions. Soundness says that if the test accepts, then what I had must have been a good solution. In other words, if the solution was not good, it was far away from a good solution, I should reject it. Okay? And in general, the existence of a certain test like this immediately implies unique identifiability. Why? Why does it imply? Well, I just get a brute force algorithm for free, right? I just go over all possible solutions. Okay. Now it requires some effort if your solution is not in a bounded space or whatever, but just permit me. Right? Imagine that you knew some a priori upper bound on the mu-i's. Then you just like discretize the space, go over all possible means or whatever, right? And you apply your test. Okay. If the test, that there is some solution on which the test will accept. And that wherever it does accept, you found a good solution. So at least you have an algorithm. So I'm saying this kind of a verification method for solutions in the context of statistical estimation problems immediately implies unique identifiability. Okay? But it in general does not give you efficient algorithms. What we'll see today is if we prove the soundness in some simple enough system of proofs, Okay, and operationally speaking, it would mean that you only use some simple sequence of inequalities that you are used to in the context of analysis, like triangle inequality, Cauchy-Schwarz, etc., etc. If you use only simple inequalities and their combination, their composition, then these proofs will be simple in general. But in general, you have to verify that this simplicity holds. If it does, then it turns out that you can simply run this complexity theorist algorithm. This algorithm, which remember this algorithm from your complexity theory classes, where you take an NP verifier and then you basically just try to guess assignment that makes the verifier accept. And this is how we prove that. This is one method of proving that if P equals NP, then you can solve every NP problem in polynomial time. Okay, we can run that algorithm because what's our task here? We have a test. We know that the true solution will make it pass, and no fake solution can make it accept. So my goal is simply to find a solution that will make the test accept. Right? Now, in general, this is inefficient. But we'll show that if the analysis of the test was simple, it used only like some simple sequence of inequalities, then we'll be able to make this task of generating a solution that makes the test pass efficient. Okay, this is like the punchline, and then you will get an algorithm out. Okay? All right, so that's basically the diagram. Like, if there is a simple proof of soundness, then you basically can get an efficient algorithm to recover this underlying structure from the analysis of this test. Good. So I'm coming to the end of the slide part of the talk, Akash. I'll give you like a picture proof of why you should expect a test like this to exist, and then we'll move to the board and analyze the test. Okay, good. So what's our goal in the present context? So we were given a bunch of data points that were distributed as a mixture of identity covariance Gaussians with unknown means. Our goal is not to cluster the data. Our goal is not to find the means. Our goal is to take a purported clustering of the data and check if it is a good clustering. Okay? Does this make sense? That's our goal now. Okay, so let's focus only on the one-dimensional problem. So D is 1 now. Okay? Let's also imagine, to like reduce notational overhead, that each cluster was of size exactly n over k. So it had exactly 1 in k points instead of like being around it because of sampling. Okay? Still okay? All right. So each cluster has n over k points. Everything is in one dimension, so I can draw things. So let's say we have a mixture of two Gaussians. So when there was a red cluster and a green cluster. Okay? And notice that I drew them so that their centers are separated, and that's this delta, right? Like the means are separated, so it's a mixture of two Gaussians in one dimensions with means separated by delta. Okay, so now I need to do some. So you're given like some purported cluster. Okay, it could be a bad cluster like this. It could include some points from red and some points from green. I want to look at this cluster. I want to do some check on it and decide whether this is a good cluster or not. Okay. Now, of course, if you knew the boundaries of red and green, you can do this trivially. But of course, you have to do it. You have to do it without seeing the colors of the points, right? You don't get to see what this red and greens were. You just see like this blue cluster. You have to identify by just the structure of the points appearing inside this, this bucket, whether it's a good cluster or not. Does it make sense? Okay, so what would you check? What somehow looks different about this blue cluster that somehow is like, what's the property that seems to be satisfied or not satisfied by this blue cluster that will be satisfied by the red and the green, the original true clusters? What do you think is different about this? Huh? Points are not mere mean. Yes, correct, exactly. So, sorry again? They are large gaps. Yes. Okay, let's yeah. So both of you are right. Basically, it means that these points seem a little bit like spread out, right? Like that's the intuition. It seems apparent with the diagram, while the points in a true cluster seem huddled together. They're kind of close together. So I just have to find out some measure of how well separated the points are, or like how much the deviation around the empirical mean is, like to take Pandupriya's idea, right? And if we can somehow formalize this, we'll have a test. Okay, that's exactly what we'll do. Okay, good. So by the way, I should say that this is you're relying on the fact that Gaussian clusters will look closer together, so that you're relying on some kind of a concentration property of Gaussians here. Okay, right now it's not important, but eventually we'll see that we'll have to think a little bit more about this. Okay, so yeah, that's my cue for going to the board. And I was told that we cannot move the slide, we cannot move like this screen up. So I'll just let it be there. Okay, so let's try to formalize this. Let's try to formalize this test and the analysis of it. Okay, so let's just remember the parameters. I'll not write down the definitions, but I just try to remind them what you saw on the slides. So remember, K was the number of components, D was the dimension, N was the number of samples. Oh, okay, all right. Good. So let's also set some notation. Let's say C1 star, C2 star, CK star are the true clusters. And remember that all the distinct means were separated by at least delta. Okay, good. Okay, good. So now oh wow, okay. All right, so yeah, let's try to design a measure of how close-knit a given set of points is. Okay, first we'll use the information that we had. We knew that all clusters are of size exactly n over k. So if a purported cluster is not of size n over k, you reject. Okay, let's use that information that was given to us. So a good cluster we know is of size n over k. So our first test would be to check that its size is n over k. Let's now try to design a measure of how close-knit a cluster is. So we'll use, there are many ways to do this. I'll use moments, okay? So let me recall what this idea of moments is if you haven't seen them before, and then I'll tell you how they capture how close-knit a cluster is. So, for a scalar and a variable x, the tth moment is simply the expectation of x to the t, okay? So you might have seen this before. If x is a Gaussian random variable, we actually know what its moments look like. We are in 1D, so n0 identity is just n01, right? And the expectation of a standard Gaussian, the tth moment of a Gaussian is 0 if t is odd, and if it's even, it's the product of odd numbers less than t. Okay, so I'm going to call this t minus 1, 2 factorial symbols or double factorial. That's it's called. I mean, whatever, we'll stick to it. You should think of this expression as roughly t to the t over 2. Yeah, that's the way to think about this. Okay. So we know the moments of a Gaussian. Okay. And if you look at this set of points that we were drawing, right? Here is what we can do. Let's say, so we have this fake cluster, this cluster C. Let mu be the mean of the points in C. So let's call it x chosen at random from C, the mean. This just means the empirical mean of the points in the fake cluster C. Then we'll do what Padmapriya was suggesting. We'll take points in, C, subtract its empirical mean from it. Let's maybe remember that it was the mean of C, right? Then compute the tth moment for a parameter t as x is chosen at random from C. Okay, do you see what I'm doing? Right? So what I'm computing is the empirical tth moment of C around its expectation. Okay? And intuitively, if you think about it, you're saying that as you make t larger, you're basically penalizing deviation from the mean more and more. Like that's the intuition, right? Like you are saying, I'm summing up or I'm averaging higher powers of the deviation. So as t goes larger, I'm actually saying that I'm penalizing your deviation from the mean more and more. Okay, and so in some sense, you should think of this being small as like some sense, some indication that the cluster is well knit. Okay, we know exactly how well knit a true cluster can be. The true cluster was supposed to be Gaussian, right? We know that Gaussian's moments behave like this. So we know what would this expression look like if I was to compute it on one of the true clusters, like the red and green points. We know, for example, that this won't be much larger than, t to the t over 2. Okay? So our test, just to make it now precise, our test would be, so what does the test take, by the way? The test takes input, this fake cluster C and the input points x1 through xn. Given such a C, it checks that the size of C is what it is supposed to be. And, there is a parameter, so let's call it t test. And I check that the tth moment is, not too much larger than t to the t over 2, which it was supposed to be if it was the Gaussian. Okay? Why am I involving this 1.1 here? Well, for a Gaussian distribution, that is how the moment is supposed to be. But really, I'm comparing empirical moments. So for a true cluster, there's going to be like some deviation, some sampling error, and saying that, let's not worry too much about the issues of sample complexity. Like everything is like easy, but we'll not focus on that. We're just giving ourselves some room here, saying that, just like extend this a little bit, and that will take care of the sampling error. This in general, like, should be satisfied with high probability if, this was a true cluster. So, this will be our test. Does it make sense? So that's it. I've given you my test. Okay, this is actually our test, and we'll show that this test actually works. Okay? Yeah, that's exactly what we'll see. So yeah, I haven't told you. I'll give you a precise theorem soon. Yes. Okay, so let's try to analyze this test and see how good it does. Okay, and then we'll try to answer Jay Kumar's question. So first, let's do the easy thing. We kind of already discussed it, so I won't prove it in all details, but I'll just say it. So if C is one of the true clusters for any one less than I less than K, then C passes the check with high probability over the draw of Xi's. Okay, this is simply saying that, why is this true? Well, because, with high probability over the draw of these points x1 through xn, any true cluster would have the property that if I subtract out its empirical mean from it and take the tth moment, it would look like a Gaussian. So it won't be too much larger than a Gaussian. And then, this test would clearly be satisfied. Now, I am kind of fudging a little bit. The cluster won't be exactly of size n over k, but, let's not worry too much about that. Okay? You feel fine with this? Okay, very good. So the interesting bit, of course, is the soundness, which I will prove to you. The soundness of the test. So let me write a precise statement. Suppose W indicates so W in 0, 1 to the n indicates the cluster C. Okay, this is simply setting up the notation. I'm going to write it like this because it will be useful to me later on. So like, indicate, like take the 0, 1 indicator of the cluster C. Okay, that's what W is. Let's write down, the intersection of this cluster C with one of the true clusters. So let W of I be okay, so what am I doing? I'm looking at all the points that fall in the ith true cluster. and then summing up Wj. So what does it give me? This is basically the intersection of C with Ci star, and then I am dividing it by n in k. So it is like the normalized intersection of C with Ci star. Okay? So if I add up all the Wi's, what do I get? Just so that I know you're all there. You get 1. Okay? It's a normalized intersection, because Ci stars cover the whole set of points, Wi's, if I add them all up, I get 1. Okay? With C, like W is the indicator of the cluster C that you're checking. C is like a purported cluster given to the test, right? Ci stars are the true clusters. So W of I measures the intersection of C with Ci star and divides it by n over k, the size of the clusters, right? The fraction of points in C that come from Ci star. Okay, so now, so we know that Wi's add up to 1, and if W happened to be one of the true clusters, what would be true? Well, one of the Wi's would be 1 and everything else will be 0. So the max of Wi's in that case would be 1. Okay? So this lemma says that if W passes the checks, then max of Wi is at least okay, so it's going to be very, very close to 1. Okay, so this is what I'm going to prove to you. Okay, does it make sense? It's basically, so hopefully you see that it encodes, what we were trying to encode. Okay, so we'll see in the proof, we'll see how to set this parameter t as a function of the separation delta. Okay. The completeness says that, if I do this check on any of the true clusters, then it must pass with probability 1 or like probability close to 1. Oh, you're saying what did I write here? Does that make sense? Sorry. Good. Any other questions? Cool. Okay. All right. So, okay. So let's try to do this argument. It's elementary, and it's like in some sense, if you remember, if you knew all the black box part of this lecture, this lemma that I'm going to prove is basically your entire algorithm. Like nothing else is the original work. Okay. So remember, like what we are doing here, essentially, eventually, is the new part. Okay. So let's try to prove this lemma. So, okay, so here's the proof. So we already saw that the sum of Wi's is 1, okay? Good. So what I will end up proving, in fact, is that max of Wi, that not only max of Wi is large, I will end up proving that sum of Wi square is at least 0.99. Okay, so I'll actually prove this. Can someone immediately see why this statement implies this statement? Yeah, you all say this, right? If the sum of the squares of W's is large, it must be that the max is large because the sum of W's is 1. Okay, so I'll actually just prove this statement. Okay, good. So here's the proof. So, all right, what do we know? We know that the expectation yes. So W is just the 0, 1 indicator of the cluster C. Yeah. So W, the cluster is a subset of points in the input sample. So W simply is like Wi is 1 if I is included in C and 0 otherwise.
Oh, I see. When you say small W passes the cluster first.
The cluster C. WI, the notation, sorry. Yeah, that's terrible actually of me, but let me clarify. W sub I means the ith coordinate of W. W of I means the intersection of C with Ci star. Sorry.
You're only using that.
Yes, yeah. Yes. Sorry about that. Okay, good. Yeah, so this is what we know. Why do we know this? Because, W passes the checks. Right? Okay, good. So I claim that it suffices to prove that if I look at all pairs that are unequal, all pairs of clusters that are unequal, the W of I is what is being used here, okay? So this is like saying the normalized intersection of C with the Rth cluster, the R client cluster, right? I claim that this is at most 0.01. Okay, why is this enough? Again, to keep everybody on their toes. Why is this enough? I claim that this implies this statement that we're interested in, right? Because, yeah, these are the cross terms. Good. So you're all there. That's amazing. Okay, so
Why is the sum of W parentheses I, why is that 1 and I?
because I normalized it.
Every J is in one cluster.
No. So remember, like C has size n over K. So this is the intersection of C with Ci star.
Okay. I guess what I'm saying, Ci star is the ith cluster.
Correct.
So if you sum over all I,
Yes.
so basically.
If I sum up all the points, yes, but I'm only summing over points in C, right?
Yeah, right. But if you sum over all i's, then Wi will basically sum over every coordinate from 1 to n.
Yes, it is summing up every coordinate of W from 1 through n, which means you get sum of, which means you get like the sum of the elements of the characteristic vector W, right?
Which is n.
Which is n over k because C is of size n over k.
The I is not
Does it make sense? Yeah, please feel free to stop me. Yeah, I guess I haven't chosen the wisest notation. Yeah, in my defense, I chose this notation many years ago, and I'm now. Huh? Okay, all right. So my proof will use like one super silly inequality, which I'm going to call the silly triangle inequality. Okay, this is a major inequality that you all should know. The silly triangle inequality. Okay, you'll see what is silly about it in a second. The silly triangle inequality says that a plus b to the 2t is at most 2 to the 2t, a to the 2t plus b to the 2t. Okay, that's the only inequality I'm going to use in this proof. I'm going to use this inequality twice, and that's it. Okay. So remember, I want to prove this, and I only want to use this inequality. So I'll go that side and write down the whole proof. Okay. So let's analyze like this some of the cross terms. Okay. Wow. Okay. So here's what I'm going to do. I'm going to do the first and only creative step in this proof. I'm going to say that this is at most Why is this true? I'm simply using that for every r not equal to r prime, and the true means mu r and mu r prime, their difference must be of magnitude at least capital delta. Okay, so I'm using that for any r minus r prime, mu r minus mu r prime to the 2t must be larger than delta to the 2t, right? So I'm multiplying each of these expressions by something that is bigger than or equal to 1, so the inequality holds. This is the only creative step in the proof. Everything else would be keep applying triangle inequality until something gives. Okay? All right. So let's apply the silly triangle inequality now. Oh, and maybe remind ourselves that these are the true means by writing stars on them. You see what I did? Like, I in between I added and subtracted mu sub c, okay, and then I applied the silly triangle inequality. Okay? All right? So this is kind of nice because if you think about it, it decouples R and R prime. Like WR actually only couples with this guy, right? And WR prime couples with this guy. So I can actually now think of this as just two copies of the same expression. Okay, you're all good with this? Right? I'm just observing that if I sum up, like if I look at this first term here and sum over R prime, I get basically at most 1. I'm actually summing over R prime which is not equal to R. So I don't get 1 in principle because one of the terms is missing, but it's still at most 1, right? And so I get that the first term gives me just WR mu R star minus mu C to the 2t, the summed over R. The second term gives me the same thing but summed over R prime. They're both the same. So I just lost a factor of 2 here and I got the same expression. Are you still good? Okay, we're going to do this one more, like, we did one application of silly triangle inequality so far, right? We're going to do one more and then we are done. Okay, so, all right, so like so far, we've been working, so we haven't opened up like these WIs again. Like, so far we've been working with like cluster intersections. Now I'm going to open up these WRs, okay? I'm going to write it as what did I do here? Oh, actually, and I should be a little bit careful. Let's call this, okay. The notation is our biggest enemy because nothing is actually happening. So let me explain why nothing happened. So, here, look at like what's happening when I fix an R, okay? And I have the term WR that multiplies mu R star minus mu C to the 2t. I replace WR by what its meaning is. WR is basically like, the normalized intersection with the Rth true cluster. So I get the sum of Wi where I falls in CR star. Okay? Now I do this for every R. Okay? Then I get to replace all the WRs by like basically the sum over points. But then if I look at a given point I, it should come multiplied by its corresponding true clusters mean minus mu C to the 2t. That's what this is. Sorry, what? What is gamma? Oh, R. I'm sorry. I'm so sorry. R is the index into the true clusters. Yes. CR star is like the Rth true cluster. R of I, yeah. R of I means the true cluster index that the ith point lies in. Okay, yeah. See, in the slides, I would have defined this. Okay. All right. Okay, good. No problem. Okay, so, oh, wow. Okay. So now, I'm going to apply the silly triangle inequality once again, and then I think we are done. So why do I apply that? I mean, in some sense, the reason I'm doing it is because I want to bring the xi's back into the game. Okay, so I'm going to add and subtract xi here now. and apply a silly triangle. Okay, so I'll say I'll continue here is at most 2 to the 4t plus 1 over delta to the 2t k over n. Okay, let me write this for 1 second and then I'll erase it. Okay, you're still good? I applied silly triangle inequality and I separated the two expressions because I'm going to play with them a second. Okay, what did I do? I just added and subtracted xi here. Then I applied silly triangle and I just wrote down the two terms I got. Okay? Now is the time we use the fact that the true clusters have bounded moments and the fake cluster passes our moment checks. Okay? Look at this guy. Okay? Yeah, let's call it R of I. Okay, so first I'm going to use the fact that WIs are only non-negative. So if I erase them, I don't change the inequality. I'm only making the expression larger. Okay, so now what do I get? What is the distribution of xi minus its corresponding mean? They are Gaussians. So forget this k. I have one like k times 1 in n average of xi minus its mean to the 2t. Okay, so I have an average of a standard Gaussian. It's a standard Gaussian because I subtracted its mean from it. Okay, so I have an average of a standard Gaussian. The 2th moment of a standard Gaussian is empirical 2th moment. It should basically, oh, did I make some? Yeah, okay. I think I switched t to 2t, but we'll continue with 2t here. Okay, no problems. Okay, so this is like the 2th moment of a standard Gaussian, right? Up to a factor k. So I'll say this first term is at most 2 to the 4t plus 1 over delta to the 2t times k times this 1.1 slack, I'll keep it around for now, times 2t to the t. Okay, it was t to the t over 2, but for some reason in this proof I'm doing 2th moment, so whatever. Okay, what about this second term? Well, for this second term, let's again examine this expression. Okay, what is this expression? It's the empirical 2th moment of the fake cluster or like the purported cluster after centering with its own mean. And we pass the checks, exactly. So this expression also has to be small. How small does it have to be? Well, it has to be like that of a Gaussian. Sorry, there's no k over n here. This is 1.1 times 2t to the t. Because w's sum up to n over k and I'm normalizing by the size of w. Like the reason we encountered a k here is because we erased the w's. Okay, so yeah, we don't lose, not that it matters, but you don't lose a k there. Okay, you all good? So now, let's look at this bound. Like, let's ignore the constants now. I mean, we carried them along for long enough time. We can call this 1.12 if you like for a second. And then, this is at most 2 to the 4t plus 3, I guess, delta to the 2t times k times 2t to the t. Okay, so now let's answer Jay Kumar's question. What do I need this whole expression to be? I need it to be at most 0.01, right? So in order for it to be at most 0.01, I need to make sure that t is large enough as a function of delta so that this expression is at most 0.01. Okay? So let's that's also true. Yeah, let's plug in some numbers and see what happens. Also true. All of that is true. Let's first understand the case of like t being a constant. Let's say like t equals 2. Okay, when does it work? When is this expression true? What delta do you need to have in order to make this expression at most a constant, when t is a constant? No, let's say, let's make it simple. Like, let's say t equals 1. Okay, so this is delta squared. I have some constant over here. So delta square, k over delta square times a constant needs to be at most 0.01. So delta needs to be at least square root of k. Okay, up to constants. So constant t implies I need delta to be at least square root k. Okay, now let's go to the other extreme regime where we want to tackle like the statistically minimum separation of root log k. Suppose delta is root log k. Okay, then what happens? Well, I have k over log k to the t, right? Like that's root log k to the 2t. And I have like, let's again ignore constant. So, we have this. I want this to be at most 0.01. Okay, suppose I choose t to be log. So actually, let's maybe have c log k so that I don't run into issues. Okay, and choose t to be log k. Think of c as a large constant. Think of t as log k. Then what do I get? Do you all see that I get like some c to the t remaining after I? Okay. So basically, I need t to be log k to handle the statistically minimum separation case. And at constant t, I need root k. At like t equals 4, I match Santosha's result from 2004. At t equals 1 in epsilon, I can make delta, which is k to the epsilon. Okay? Does that answer your question, Jaikumar? Yeah, that's true. That's actually a very astute observation. There is a different part in the formalization of this proof where I don't actually get to enjoy that win. You're right that this lemma shows as if I'm winning at a little bit better than log k, but unfortunately there is a different part where it's very nice, very, very good question, yeah. But at least you see the brief, like the rough idea of where this t is going to come from. It's basically like if delta is k to the epsilon, you need to choose t to be order of 1 in epsilon in order to make this expression work out.
T double factorial by t to the
t to the yeah.
Is that where you get around this? You don't take the benefit of this log?
No, it's a different part of the argument actually. So okay, this is so far. Even though I promised you that we are doing the main step, which I'm not lying. This is the main step, but this is 1D and things like that, and so there is some additional losses. Yeah. So this part is like, as it's very transparent. There is no loss here. It is what it is. Okay. So you're all happy with this. So what have we done? It kind of looks like I'm cheating you. What have I done? I have given you a proof of moment identifiability. I've given you a proof that this test that we designed of well spreadness actually works if there is sufficient separation. And like, depending on the separation, I can tune this number of moments to actually use in order to make this test actually succeed. Okay, that's what we've done. Okay, now what do I have to argue to you? I have to give you an algorithm somehow. I have to relate this analysis, which really did nothing, like, which applied the silly triangle inequality twice. I have to show you that this analysis actually inside of it has an algorithm. Okay, that's what I'm going to do now. Okay, good. So I have like about 12 minutes, so I'll start the setup and then we'll do like cooler stuff in the remaining part. Okay. Good. So I gave you a proof of soundness of this test, right? What I want to do next is explain to you the precise sense in which this proof of soundness is simple. Okay, I'll try to formalize the notion of simplicity, explain to you why this this particular analysis of soundness is simple. And then, I'll show you, how it fits into an algorithm. Okay, very good. So let's look at, the kind of soundness proof we did here. So I guess let's let this part remain, and I will erase maybe the left part. So, if you look at the proof of soundness, it has the following structure to it. What we are proving is like, some inequality about some functions of this variable W, right? So, there are some variables W1, W2 up to Wn, right? And what we really proved is that if W satisfy some conditions, namely the conditions encoded as passing of the checks, then it must also satisfy some new inequality, namely this inequality. Right? So even though it's written in notation in terms of W of R, remember that W of R are just like linear forms in Wi's, right? So everything is just like a function of W. So you're saying, if W satisfies some conditions, namely the two checks, then some new inequality follows. That's what it is. Okay? So in fact, if you see, there is more that is true. The hypothesis of this inequalities, a hypothesis of this theorem is a bunch of polynomial inequalities or equalities in W. Right? This, for example, is some Wi equals n over k, right? This is an inequality, okay, in W. Notice that x's and mu's, etc., they're all constants. Right? We are viewing it as some claim about every W that satisfies some checks, satisfies some other inequality, right? So these are all like fixed numbers. Why are they fixed? In particular, they were given to us, right? Like x's were given to us. Mu c was not given to us, but mu c itself is a linear function of W. Remember what mu c is? Well, mu c is right? It's the empirical mean of the points indicated by W. So all I'm observing is that what we just analyzed, what we just proved is if W satisfies a bunch of polynomial inequalities, namely this equality and this inequality, whatever, like, after you plug in this expression from UC inside of here, then it satisfies a new inequality, which is this. Okay. Now I want you to observe something about this because we'll come back to it. The assumptions, the inequalities that we assume on W are written down in terms of the data that we saw. Okay, the inequalities I'm writing down here are functions of xi's that we saw. The inequality that we concluded, on the other hand, has information about the true clusters that we certainly did not have in the beginning. I mean, that's the whole game. That's what we're trying to find out, right? So we are saying if W satisfies some inequalities, which can be written down by just looking at the input data that was given to you, then it satisfies a new inequality, which somehow tells us how W behaves with respect to the true clusters. So even though this is a polynomial inequality, we don't quite know what this CR and CR primes are. We can still write down this inequality. We don't know, algorithmically speaking, what these CRs and CR primes are. Okay. Anyway, for now, the hypothesis and the conclusions are both polynomial inequalities in W. Okay. So what we're going to do is formalize a notion of simplicity that applies to such arguments, such claims. These are claims that say that if a certain system of variables satisfies a bunch of polynomial inequality or equality constraints, then a new polynomial inequality or equality follows. We'll try to formalize the notion of simplicity of proofs of such statements. Okay? So this is the notion of sum of squares proofs, which I will now tell you about. You can think of this as like a formal way to evaluate how simple this proof is, and I'll tell you exactly how it does. Okay. So in general, let P be an n-variate polynomial, just like we had in our case. In our case, the polynomials were functions of w1 up to wn, so they were n-variate polynomials. We say that Px has a SOS proof of non-negativity if Px can be written as a sum of squares of other polynomials. Okay, so this is just a definition, but it's an important one. So let me like spend 30 seconds on it. We're saying like we are interested in proving that a multivariate polynomial is non-negative. Okay, there are many methods of proving this in principle, right? There are many ways you could try to prove this, but there is one particular method that I'm very interested in. Okay, and you could think of like the mantra of this method as prove inequalities by actually establishing identities, establishing equalities. Okay, because the best inequality is an equality. Okay, so we're saying one way of proving a polynomial non-negative, it's not always possible, maybe it's never possible, but if I can write P as a sum of squares of other polynomials, then it's immediate that P is non-negative because squares of polynomials over the real numbers are non-negative, right? So if I could say you give me a Px and I could tell you this expression, I could tell you this SIs, then and I claim that Px is sum of SI squares, then you can immediately verify that this identity holds by comparing coefficients on both sides. And once you confirm this identity holds, you are immediately convinced that Px is non-negative because you've confirmed that P is a sum of squares. Okay? Such a proof of non-negativity I'm going to call a sum of squares proof. Okay? So let me give you examples. So I'll prove some very hard inequalities now for you. Here is like a famous fact. This bivariate inequality seems to hold. And how might I prove this? Well, I observe that it actually equals a minus b square. So I've taught you how to prove this bivariate polynomial inequality. Okay, it's an unconstrained bivariate inequality. Very good. So I've proved it by reducing it to an identity. I gave you the sum of squares. This is sum of squares proof. Very good. Let me actually give you a proof of a slightly more complicated inequality. If you think about it, this is the t equals 1 case of the silly triangle inequality. How do I prove this? How do I make an identity out of it? Yes, exactly. So should have left some space. Yes, that is correct. Astute.
I was wondering if you put that because that one also has a that one
I put that because I grew tired of writing minus ones, which is weird because I wrote plus ones later on.
But all of Jensen can be, so Jensen just gives directly, but that cannot give.
So Jensen, in principle applies to things which are not polynomials because it applies to arbitrary convex functions. So I don't want to be as general as that. But yeah, if you apply to polynomials, yes. Yes. Okay, so I've proven to you the t equals 1 case. Actually, you can confirm. So I will not maybe prove this to you. I mean, I think in my notes I guess proved it at some point, but I will not prove it to you. The proof of this is actually not too much harder. Okay. In order to convince yourself that this is not harder, I implore you to prove the t equals 2 case. Okay. Do the t equals 2 case and you'll see why you should be able to do it for any t. Okay. So, we've just proven, or we've just at least convinced ourselves that the silly triangle inequality has a sum of squares proof. Okay. So, let me give you some more examples. Example 4. This is a 2n variate inequality, if you will. And it also has a sum of squares proof. Does someone remember why? What's the name of this inequality? It's the Cauchy-Schwarz inequality. Yeah, correct. And that fact has a name. Do you also remember the name? It's called the Lagrange identity. Is that what somebody said? Yeah. Okay. So Lagrange was one of the first people to provide sum of squares proofs. In particular, look at this. Like, he was interested in algorithm design in the 1800s with the sum of squares method, and he needed the Cauchy-Schwarz inequality, so he proved it. Good. Okay. Good. So you have a sum of squares proof of this inequality. Okay. Good. So yeah. I think these notes were written for a much longer thing where I have like a list of these jokes that I continue to make. Apparently, I should stop at this point. But do all inequalities have sum of squares? I mean, we seem to be doing pretty well. We could go on for an hour. We could just like play this game of coming up with inequalities and proving it in sum of squares. Do all inequalities have sum of squares proofs? In particular, are all non-negative polynomials sum of squares? And this was a question that a great algorithm designer named Hilbert was interested in. Yeah, he asked this question, and we learned the answer over time. So we know that all univariate non-negative polynomials are sum of squares. It's an exercise, you can prove it. I'll take 2 or 3 more minutes so that I stop once I'm done with proofs. Okay. Okay, so all univariate polynomials are sum of squares. Does anybody see an immediate proof? Correct. And yeah, exactly. It's non-negative. Yeah, very good. Yeah. So if it is 0, just remove the zeros, and if it is non-negative, like if it is strictly non-negative, strictly positive, then its roots must appear in convex, complex conjugates, and then yeah, their products will be squares. Good. Yeah, that's a proof. If P is a multivariate quadratic, it also is a sum of squares. You can prove this. This is P is the DNS of quadratic forms, if you will. In general, this is it. Okay, there is one more silly case, but doesn't matter. But basically, it's essentially speaking, these are the only cases where non-negative polynomials are sum of squares just always. Okay, univariate case or bivariate, like multivariate but quadratic. Okay, that's it. So in fact, it was a question that Lagrange asked after giving a sum of squares proof of the Cauchy-Schwarz inequality, whether every non-negative polynomial has a sum of squares proof. Hilbert actually disproved him in 1889. And actually, it's kind of crazy, but Hilbert's proof was non-constructive and complicated. But there is a 1961 construction of this so-called Motzkin polynomial. It's very simple polynomial. It's bivariate. It has 4 monomials. And you can prove it's non-negative by AMGM inequality, but it doesn't have a sum of squares proof. Okay, so it's a very, very simple example of a non-negative polynomial, which is not sum of squares that people found in 61. But Hilbert knew it exists in 1889. And then there's like, okay, there's a long story, but Hilbert basically asked whether every non-negative polynomial can be written as a sum of squares of rational functions. There's an appropriate way to ask this question, and it turns out that question has a positive answer. It was Hilbert's 17th problem. It was resolved by Artin in 1927. So anyway, there's a long history of algorithm design using sum of squares. But anyway, so I'll just take 2 more minutes to explain one more idea, and then I'm done. So these were all unconstrained non-negativity questions. Okay, but we will in our case we'll deal with constrained inequalities, because we are not trying to prove some fact about all W. We're trying to prove facts about W's that satisfy some additional constraints. They are constrained inequalities. They only hold if the underlying variable satisfies some other polynomial inequality constraints. Okay, so again, I won't be super formal, but let me observe that if A is A square, a polynomial constraint, and B is B square, then the following fantastic inequality holds. How would you prove this? Well, I'll prove it by writing down this inequality's proof, but then I have squares, so I say plus A minus A square plus B minus B square. Okay, so hopefully you agree that this is an identity. Okay, you can do by comparing coefficients. And moreover, I claim that this identity provides you a proof that if A is A square and B is B square, then A plus B minus 2AB is non-negative. Why is that? Well, because I have a square and some terms that vanish when the constraints hold. Okay? So in general, such an expression is a sum of squares proof of a constrained inequality. Okay, it just means that I write down the inequality as, I write down the polynomial I'm interested in as a sum of squares plus something that is a linear combination of products of the constraints that must be satisfied, because that part will then vanish whenever the constraints actually hold. Okay. One last idea. Given such inequalities, I can now measure how complex their proof is. So far, we've been just writing down the proofs, but you can now ask how difficult is this proof? And in this system of writing proofs, we can have a natural measure of difficulty, which is the degree of the largest polynomial that appears on the right hand side. Okay, so this is a degree 2 proof, this is a degree 4 proof, this is a degree 2t proof, and so on. So now you know how to account for the complexity of such proofs. We have given a very simple definition of it. You all good with this? Good. Okay. So all right. So I don't want to define for you constrained sum of squares inequalities where the constraints are inequalities. There is a very natural way to do it. I will recommend that you just think of the constraints as equalities always. You can always make the constraints equalities by just introducing some slack variables. Okay. So let's not worry about inequalities at all. Every constraint is always an equality for us. Okay, good. So now, okay. So I'll state one fact and then make this observation. So suppose you have a bunch of polynomial constraints, and there is. So I'm going to write this symbol, and I'll tell you what it means. If I write D1 here, this notation means that there is a degree D1 sum of squares proof that establishes that whenever P1 through Pm are 0, then Q1 is non-negative. Okay, and you know the meaning of this sentence now. Okay, suppose it is true, and suppose I have this original hypothesis, and now I even add this additional hypothesis that I derived in the first line. And suppose there is a degree D2 proof that assumes the conclusion of the first statement here and derives a new statement. Then none of this is surprising, but I'll say it anyway. There is a D1 times D2 degree proof that derives Q2 bigger than or equal to 0 just from P1 through Pn. And what I'm telling you is composition of sum of squares proofs, right? Like I'm saying, suppose you started doing this reasoning in sum of squares. From P1 through Pm, you derived Q1 non-negative in degree D1. Then you assumed Q1 and derived in degree D2 a new consequence. Then you can string together these consequences and the degrees multiply. Okay? You should think of it as like, when you do a proof, you basically, apply reasoning in sequences. So you're composing, what you derive in the previous steps, right? This statement is telling you how the degree of the proof varies when you compose statements. Okay? With this, we are ready to observe that what we did is a sum of squares proof. Why is that? Well, I told you that the silly triangle inequality has a degree 2t sum of squares proof. I applied it twice. Okay? And those were the only inequalities I actually used. Okay? Like the other inequality was an inequality of constants. It was an inequality of this constant is bigger than this constant. Okay? That has like, yeah, that's just an inequality of constants. It's not a polynomial inequality in our variables. So this proof involved two applications of silly triangle inequality. So what is its degree? T squared, or like order t squared. Yeah, that's it. Okay, so we'll stop now. We just observed that we gave an order t squared degree sum of squares proof of the soundness of our test. And then, when we come back, I will show you how it applies an algorithm.